Right, today I'm going to give some feedback on the Aqueous Equilibria assignment. Question number 1, it gives you the pKa, and it's asking what is the acid to base ratio that's needed to prepare a buffer with a pH of 4.50. Okay, so what we're solving for is this ratio. Okay, so we're given the pH that we want. We're given the pKa. We subtract pKa from both sides, and that gives us negative 0.24, and that is the log of the ratio. Okay, the inverse of the log is 10 to the power, so it's 10 to the minus 0.24, and that would give you a value of 0.575. That's for the base to acid ratio. Okay, if you calculated the acid to base ratio, then it's 1.74, just the reciprocal. Either answer we will accept. Okay, part B, again, we used the buffer equation for that. And we would substitute 0.45 for the base, 0.5 for the acid. Okay, the pKa is the same. And then if we solve for the pH, it's 4.69. Okay, part C. If we take concentration times volume, we get millimoles. Right, so 0.45 millimoles per milliliter, which is the concentration of acetate, times 100, we get 45. And for the acetic acid, it's 0.5 times 100. And since the volumes of these are the same, those we can actually divide those out and just work with millimoles. Okay, so 0.005 moles is 5 millimoles. And if we add sodium hydroxide, that is going to increase the concentration of conjugate base, and it's going to decrease the conjugate acid by the same amount. Okay, so this will be 45 plus 5 in the numerator, 50 minus 5 in the denominator. Okay, if we perform this operation, then take the log of it, and then add that to 4.74, we get 4.79. Okay, you can see that the pH went up because we added more base, but it didn't change very much. Okay, part D is the same idea. This time we are decreasing the amount of base and increasing the amount of acid. Okay, so solving for this, we get 4.64. Okay, and again, you can see that the pH went down, but it didn't change by very much. Okay, question number 2. Use the values of KSP to calculate molar solubilities for copper 2-phosphate. Okay, this is, we would have, when this dissolves, it produces 3 copper 2 ions and 2 phosphate ions. And the KSP would be 3x cubed, 3x the quantity cubed times 2x the quantity squared. If we combine those terms, that's 108 times x to the 5th. Solving for x, we would take the KSP divided by 108 first, and then we take the 5th root of that. So that's 1.67 times 10 to the minus 8th. Okay, this one we would do the same way. but here all we have to do is take the square root. This is a 1-to-1. Silver is X, iodide is X. X squared is equal to KSP. Okay, part 3, question number 3, we're going in the opposite direction. Okay, this time we're given solubilities, and then we are asked to calculate KSP. Right, this is a 1-to-1, and so all we have to do, this is cadmium is X, carbonate is X. Okay, so we just square this, and we get our KSP. For part B, okay, we calculate the molar solubility first. We take 4.34 grams per liter times 1 mole divided by 367.01 grams. Okay, so grams divides out, and we end up with moles per liter, or molarity. Okay, so that is X. KSP is 4X cubed. Lead is X. Bromide is 2X. In the KSP expression, we would square the 2X, so combining terms, we get 4X cubed. And our KSP then is 6.61 times 10 to the minus 6th. Okay, question number 4. This is a question involving the common ion effect. Okay, here we have strontium fluoride dissolving, but then we've added extra strontium by adding strontium nitrate. Most nitrates are soluble. Okay, so our KSP, okay, let's make that 10 to the minus 9th. Okay, so our KSP is 2.6 times 10 to the minus 9th. If we didn't have the extra strontium, this would just be X times 2X is quantity squared. Okay, so X is just from the strontium fluoride dissolving, and the 0.01 is from the extra strontium from the strontium nitrate. Okay, we can assume that X is small, since 0.01 is much larger than 2.6 times 10 to the minus 9th. So we can neglect that, and this simplifies. So we divide both sides by 0.01, and we divide both sides by 4, take the square root, and X is 2.55 times 10 to the minus 4th. All right, part B, we do the same way. Okay, without the added fluoride, this would be X times 2X the quantity squared. Okay, so this is the concentration from the added fluoride, from the sodium fluoride. And again, let's assume that the 2X is small. And this simplifies. Okay, so we'll need to take we'll need to take 0.01 and square it. Divide both sides by that squared quantity, and then that's our X. So 2X is 2.6 times 10 to the minus 5th. Okay, question number 4. will a precipitate of barium sulfate form when a solution of barium and a solution of sulfate are mixed? Okay, this is the KSP. Okay, so what we need to do is first calculate the amounts of barium ion and sulfate ion. Okay, so we take concentration times volume. So we've got 0.4 millimoles of barium, and then we've got 0.18 millimoles of sulfate. And to get the concentration, we divide by the total volume, which is 400 milliliters. Okay, 100 plus 300. Okay, we have to divide both of these amounts by that total volume. Okay, so this is the Q, or also called the IP, the ion product. And that gives us 4.5 times 10 to the minus 8th. Okay, because Q is greater than K, a precipitate will form. Okay, if you only say yes or no with no calculation, there will be no credit given. Number 5, we have a strong acid, strong base mixture, titration. Okay, so we'll start out with 40 milliliters of 0.1 molar HCl. And we're going to add 0.1 molar sodium hydroxide. Okay, so if we add 20 milliliters of sodium hydroxide, okay, let's calculate the millimoles of HCl. So we take concentration times volume. So that's 4 millimoles. And our millimoles of sodium hydroxide that we have added, again, we take concentration times volume, that's 2. Okay, so 2 millimoles will have neutralized 2 millimoles of HCl. So that means we'll have 2 millimoles of HCl remaining. Okay, so to get concentration, we take that divided by the total volume, which is 60. Okay, we get 60 by adding 40 plus 20. That's our concentration of HCl. Since HCl is a strong acid, that's also our hydronium concentration. Every HCl produces a hydronium. So we take our millimoles divided by our total volume. So that's 0.0333 molar. Taking minus the log of that is 1.48. Okay, part B, we're at the equivalence point, so the pH is 7. Part C, we are beyond the equivalence point. So altogether, we've added 4.5 millimoles. And this has neutralized all of our HCl. So we'll have 0.5 millimoles remaining of sodium hydroxide. The total volume is 85, which is 40 plus 45. And so our concentration of hydroxide is 5.88 times 10 to the minus third. If we take minus the log of that, that's our POH. pH is 14 minus that, or 11.77. Question number 6. We have a solution of 30 milliliters of 0.30 molar ammonia, which is a weak base. This is titrated with a strong acid. Okay, at the equivalence point, all of the ammonia is converted to its conjugate acid, ammonium. And so the millimoles of ammonium will be the same as the millimoles of ammonia that we started with, which will be 9. Okay, I get that by taking 30 times 0.3. And if we divide that by the total volume, that's our concentration, which is 0.15. Okay, using our ice chart, the pKa of ammonium is 9.25, Ka 5.62 times 10 to the minus 10th. Ka expression is ammonia times hydronium over ammonium. We substitute these equilibrium values and we can simplify. We can assume that x in the denominator is negligible. Solving for x, we get 9.18 times 10 to the minus 6th. Okay, that's our hydronium. If we take minus the log of that, that's 5.04. All right, halfway to the equivalence point. Okay, we could set up another ice chart, but we could also recognize that we're in the buffer region, and we have converted half of the ammonia to its conjugate acid. Okay, so that means that the acid and base concentrations are equal. So this ratio is 1, log of 1 is 0, pH equals pKa. Right, benzoic acid is dissolved in water. Okay, and then taking the molecular weight of benzoic acid, we calculate the moles, or you could calculate millimoles. Okay, the concentration is amount divided by volume. Okay, and that could be moles per liter or millimoles per milliliter. You come up with the same answer. And if we solve for x, we get 2.54 times 10 to the minus third. Okay, not especially negligible compared to 0.09, but we'll go with it. Okay, the pH would be minus the log of that. Okay, so the pH is 2.60. Okay, part D. Okay, how much NaOH does it take to neutralize the benzoic acid? Okay, by the definition of equivalence point, the moles of your acid is going to equal your moles of base. So that's going to be the same number that you calculated earlier. Okay, halfway to the equivalence point, pH equals pKa, so it's 4.19 would be the pH there. Okay, if we titrate this with 0.0250 molar NaOH, what volume in liters or milliliters is required to reach the equivalence point? Okay, so we take the amount divided by the concentration, or the volume, the amount divided by the concentration. So that's 400 milliliters, which in this titration is a ridiculous amount. We have to refill the burette several times. Okay, so the total volume would be 500 milliliters. Okay, that's the 100 that you started with plus the 400 that you added. The concentration of benzoate would be amount divided by the total volume, which is 0.020. Okay, then we would enter that in our ice chart. Then we need to calculate Kb for benzoate. Okay, this is Kw divided by our Ka, which we had earlier. So that's 1.55 times 10 to the minus 10th. Okay, and then from our ice chart, we calculate X. Now, X is actually going to be our OH concentration. So if we take minus the log of that, that's our POH. Subtracting that from 14, our pH then is 8.25. Okay, since we are titrating a weak acid with a strong base, at the equivalence point, our solution should be basic, that is greater than 7, and it is.